What's up, everyone? Let's check some levels, make sure things are good. There is the unmute button. That looks good. I've got my headphones, will pop in. As you might notice from yesterday, I have a new workbench behind me. The electronics workbench is back up and running, and I'm hoping to have some stuff going on there pretty soon. Get back into some hardware hacking. On the left side here, you'll see the mill and the 3D printer are all kind of set up now. I still have to do some work on the leveling of the print bed and just some other stuff there to kind of get things all set. But we're back. It's been a long time waiting, trying to get all these things going and get this office kind of put together. So hopefully soon to come electronics projects and hardware hacking, reverse engineering, which is kind of one of the things that this was supposed to kick off was getting going with microcorruption and starting this again. I'm gonna put some music on my headphones while I work on this because I want something to put on right now, and I can't stream that unfortunately because it will get pulled for all the copyright reasons. But let's see, there is Spotify, and it looks good there. I'm going to go ahead and log back into Microcorruption. Then we'll switch over to the desktop view. For anyone that was here, it wasn't yesterday, it was maybe Sunday, Saturday, one of those days. We did some work on Algiers. Let's switch over to the desktop right now. We did some work on Algiers. We reverse engineered the free and the malloc function, and one of the things that I didn't do was really document any of the stuff that we reverse engineered. And part of the problem we had was that by the time it got to the point where we were going through with the exploit trying to make it work, I didn't really have the full scope of the implementation in my head anymore. So one of the things we're going to do to combat that today is we're going to re-reverse engineer it. I'm going to document what's going on, and we're going to write up something like C that is effectively going to be like what this, hopefully like what turned into this assembly. And that will kind of give us an idea of like, what was going on, so we can like reference that and kind of see like exactly what we have to do to make the exploit work. I assume that this is going to be used in the other challenges as well, the last like 6 or whatever. So hopefully it will be reusable. Hopefully it will be useful for us. But looking at maybe 30 lines, 40 lines of C is that I have commented and stuff is going to be a lot easier than trying to remember 100 lines of assembly and what that is trying to do, because we don't really get any kind of visual structure of the code, since it's all kind of dead code listing here. If I was in something like Ghidra or Binary Ninja or IDA, we'd have like a graph view or decompilation view, and it would just be easier to see what was going on more immediately than what we have here. And we can't really like add comments in here, unfortunately, which makes it kind of irritating, but it is what it is. It wasn't too bad to go in and add the comments ourselves, or to figure out what was going on ourselves. So I think today we'll just redo that, and we'll probably start with free because it was smaller and simpler, and that's honestly what we care about. That's where the vulnerability exists, is in that function, because we have the ability to do a metadata corruption attack, which is very similar to the glibc unlink. I believe this is the attack. And I'll jump back into this in a little bit once we get the reverse engineering part done, and I can talk about like the actual vulnerability this is, I believe, meant to replicate. And what's funny is, like, I mean, when you go into like these embedded systems and like different implementations of malloc, this unlink vulnerability is something that still exists in modern mallocs. When you're building mallocs implementations, you typically have to make some kind of trade-offs between protections and speed. In this case, we're on a microcontroller with not a lot of space for memory, not a lot of space for flash, and not a lot of processing power. So we need code that's going to be very, very fast. So we're not going to have a whole bunch of opportunity to put a whole bunch of safeguards in here. And so that's that trade-off you make in deciding like how much protection you're going to add versus how much like you want speed, and like how much you really care if someone can like exploit this. Like what's the end goal if they like pop their own thing. Like this is a lock in this case. You could like theoretically unlock a door. But I mean, if this is like some like handheld like electronics device that doesn't communicate with anything, or is just something that you like personally own, like not a big deal. So I'm popping this back up into our terminal so that we can set up tmux and get back into our document here. I think I just called it heap. I don't really have a vim config on here, unfortunately, so I'm having to type everything manually. So this is like the kind of the basics of what we figured out last week. We have some heap metadata at the beginning of our heap. I believe that this always points to the first chunk, so the first 2 bytes, and we can't see it here yet because the heap's not initialized. But we have, 8 bytes here. The first 2 bytes always point to the first chunk. We don't know what this next one is. The third 16-bit value specifies, I believe, like whether or not the heap is initialized, and then this looks like some padding because it's always 0. We can see this is like the before everything gets initialized, or this is before it gets initialized, but after the heap has been allocated. We see like this is that first 16-bit value that points to the first chunk. This is the bit to specify whether or not it's been initialized. Sorry, we don't know what this is. This is the one that is whether or not it's been initialized, and then this is what we think is maybe just padding because it's always 0. We never see it change. And then this begins like where the first chunk would be, or our like last chunk, which is just it fits this same structure more or less. Oh, sorry, this is what a chunk looks like, and this is our last one that fits like the structure. But we have a previous pointer, a next pointer, and these will point to itself if it's the last one. And then how much remaining space is left. And then there's no data ever because it's just meant to store as metadata. So I'm going to go here and we're going to set up some function prototypes. Malloc. This should be that, I believe. We'll just make these functions. I'm not going to bother with malloc, like I said, right now. We're going to start with free. Actually, we can go get these. And free. Free? Yeah. It returns void, because I think it can't fail. It like actually has an exception or something, or it like crashes, and it takes a void pointer, which makes sense. All right. So now I'm gonna set up where is login. I'm gonna set some breakpoints in here. We're gonna skip past all of this because we're just gonna do our allocations. I'm gonna set the first one at this free right here because we're gonna step into it. So I'm gonna do reset C, and I'm just gonna do A and B for our data because we don't really care right now about any of that. So I'm gonna step into this, and so again, this is saving the R11 register. We don't really care about that. R15 is our pointer coming in, so that is effectively this right here. And what this is doing is subtracting, I think, 6 from it. So R15 is 24, 24. If we look at where 24 is, that is so 0, 1, 2, 3, 4. That's the beginning of our user text. So typically, like in a malloc implementation, you have this metadata here before your user data. But when malloc returns you a value, it's going to return you. Sorry, when malloc returns you a chunk of data, it's going to give you a pointer that points here, so that you can't overwrite like any of this shit because like it doesn't want you to fuck that up. So it's going to give you a pointer to here. Now all of the malloc internal stuff is going to operate on the beginning here because it needs to read that data. So it's subtracting 6 right here, which I think this is just like literally -6 in like 1's complement or something. And it knows it's going to overflow. And I'm not sure why it chose to do that, but that's how it ended up compiling the code. In fact, I think we can just go look at like 1. 1's complement is just you flip it. So we can do that manually. FFFA. If we do FFFA, that ends up being 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then A is what is that? That's 10. So that would be if we did it like actual A, that would be 1, 0, 1, 0. So that ends up being 0, 1, 0, 1, 0, 1, 0, 1, which is 5. So it's subtracting off. Wait, did I do that backwards? No. So yeah, this ends up being like 5, and maybe it's 2's complement, and that's why it's off by 1. But yeah, so it's basically just subtracting 6 from this value, which gets us to the front of the pointer. So we see here R15 is 24, 24. It's going to end up pointing to 24, 1 E. Yeah. So the first thing we're going to do is void star chunk equals ptr minus 6. And then we're going to and. Oh, wait, what did we just do here? So we moved 4 bytes from R15 into R13. So R13 has the size. that's our size. And basically, this is anding off the last bit. So R13, it's 21 right now because that last bit, like the ones bit, is being used to denote that the chunk is in use. So see there, it ands it off. So we do size and equals FE. That is, yeah. And so then it writes this value back. PTR plus 4 equals size. Under the hood, like I might use a struct to actually point to there, and like we could write this code a little bit nicer to do that, but I just don't care. All right, and so R15 is we're gonna move to we're gonna load the thing that R15 points to, which is the previous pointer. So R15 is pointing to 24.1e, 24.1e is right here, and that's our previous pointer. Maybe we should do this as a struct. It might just make this a little bit easier. Chunk. Int pointer prev. Int pointer next. Int size t. And I guess we can clean this up a little bit. So we'll end up casting this, I guess. Chunk pointer. And this C might be a little bit off. Some of the syntax might be like slightly off, but not super important. Size equals and that's basically what it's doing. All right. So then R15, we load that into R14, and then it's R14 gonna have 2408. And then 4 bytes forward from that is going to be our next pointer. So cur prev these aren't just integer pointers anymore. They're actually pointing to another chunk. So we're loading the R4 is pointing to previous now. R14 is pointing to previous, and 4 bytes forward from that is going to be the next pointer. Next. Or sorry, no, it's going to be the size. I believe it's ends up being like that. No, we're not setting here. We're just doing the check. And 1. Chunk. All right, so we're looking at so R12 has in use, so it's going to AND this, and 0 is not set. So not 0 is correct. It ends up this branch ends up being 4524. All right, we'll go back and we'll fix that up in a second, and we'll do that other path. But basically what I think that is consolidation logic. So if you're freeing a chunk and the one that's previous to it is also not in use, it will combine the chunks back together and turn them into one big chunk that it can use later on, so that it's trying to compact the data back to, like the space back together, so that it doesn't end up having like a whole bunch of fragmentation around the heap and then not have enough space to allocate. So we're here. We're gonna load R15 is pointing to the previous chunk, so cur.prev, and then this is getting the next pointer. So 24 1e is right here, 2 bytes, so 1, 2, it points to here, 24, 3, 4. It's 24, 3, 4. This points to the current prev next. So our current one is right here. We're looking at our 24.1e. One second, 24.1e. Oh, this is current. So it's current. Current next is loaded into R14. R14 has 2434, which is right here. And we're going to move so 4 bytes from R14 into R13. So 1, 2, 3. Sorry, I'm looking the wrong one. R14 is 2434. 0, 1, 2, 3, 4. So then 4 bytes in would be 1, 2, 3, 4. So that ends up being the size here. Size. And then we're going to check if this bit is in use. So this is a forward consolidation. So we're going to consolidate into the bigger chunk at the bottom. So it does a check of the last bit on R13. R13 is this 1F9C, which is oops, 1F9C. This is 8092. This is a positive value, so it means that it's not in use. Current next size and 1. Check, consolidate. All right. So step. Now 0 is set here, and so we're going to take this branch. If so if it's in use, which it's So we're going to end up taking this jump, and this goes back to 454A. Sorry, my bitwise math is just like wrecking my brain, because all the jumps are inverted here. So this is going to be in use. If it's not 0, if it is 0, it's not in use. If it's not 0, it's not in use. If it's not in use, it goes here. Yes, so this is where we are right now. This ends up going to wherever that jump is, 4560. All right. So we add 4 from R15 is going to be our size, and that gets added to R13, which is, so we're going to add cur c size equals R13 already has C next size plus 6. So we're adding 6 to the size of the next chunk, and we're writing it to the current chunk. And that gets us through here. And that writes it to the current chunk. Then we move 2 from R14. R14 is 2434. 2434, that's the next chunk. And 2 bytes in is going to be the next field. Gets written to C next. Oh, where's my cursor? All right. So we should be here now. Step, step, step. R15 So we're writing current to our 14 points to 2434. So previous. So we're taking 24.1e and we're writing it to next previous. And then we're popping this back off, so that's our saved address. So next has already been set. So we should effectively see R15 is 24.1e gets written to 2434, which is right here. So I think what we're seeing is when we go in the next time, we end up running into this. I think I want to recheck the logic on this just to make sure that we interpreted this correctly. because we end up changing. So that, I mean, that logic is correct. The previous on here should already be correct. The next, like this next, so like the last one there, the previous should already be this. We don't care about it anymore. So I don't. Oh yeah, no, this is correct because this fixes up the one that this points to. So it's gonna follow what this was pointing to and make the previous one it. So yeah, this is correct. So, so I guess now is probably a good time to walk through like what this vulnerability is, and we can go back in time. To, from my understanding, this is like the first time this was observed. This is considered the unsafe unlink heap exploitation. This is an attack against the heap metadata. I don't remember if this was talked about in frac or if it was. Like, is this the once upon a free? Let's see. Yeah. I think this might be it. Give me one. So this is slightly different in that we have the ability to actually modify the data, and I think what they did in the original exploit was they built a fake like chunk. Give me 1 second to pull up some documentation from like my notes about this. So glib 2.6 added the checks to break this. So glib 2.5, we can go back and look at that implementation. Glibc source. I think we can find this on GitHub. This might be it. They don't start having. We're going to go find source code. 2.5. This is it. It's going to be in probably malloc.c. All right. So this is like a real vulnerability that existed in real glibc. I don't remember what year this. We can check here. I mean, this was like 2006 or 7. This was fixed. 2007. It looks like it was fixed. But basically, like the way that this ends up working, and why this is vulnerable, and the code to me a little bit different because like the glibc implementation is different than the one that we have here. But you have to imagine that we have these chunks in our heap, and we have these forwards and backwards pointers. And I'll switch this over to the terminology that they use in malloc. BK view. They'll not do that in B. It's a little more confusing, I think. But you have these linked lists of all of our different chunks, and this implementation doesn't have the concept of like a free list, but most modern ones will have what is known as a free list. So this will be a little bit different. So this implementation, all chunks stay like in the chain, whether they are free or not. So like when you free a chunk, like that space, like we mark it as not in use anymore. And when I don't know what the malloc implementation looks like, I have to go back and like reverse engineer it, but like it's gonna walk through every chunk until it finds one that fits the amount of space that's needed. And so it's going to basically walk that linked list from the very first chunk allocated until it gets to the end and either can't find a chunk that fits or it finds probably the first fit would be my guess. And free is responsible for basically trying to like recompact that data. So when you free it, it's going to try to consolidate backwards if the previous chunk is not in use, or forwards if the previous chunk is not in use. And so it's going to try to build up these big chunks that it can then carve chunks out of later. So part of the process for consolidation is if I'm at a chunk and my forward pointer is also not in use, I'm going to bring those together. So I'm going to take the size of the next one and I'm going to add 6 to it so that I get the full size. And then I'm going to add my size to it. And then I'm going to set my next to be the next pointer, and then the next previous to be myself. And that's effectively like what this does right here. Is it's keeping records, so it's keeping a forward and a backwards pointer, so it can do this. But it's saying my next back goes to me, and my current one's next goes to the next. And I know it's a little confusing, but think about it. Like you have a link right here, and you have a previous, and you have a next. And you're basically saying this previous, now my next one now points to here. And so I'm skipping over this. And then this new one that I'm pointing to, this next forward pointer, its previous is now skipping over this middle one and going back to here. So we're just skipping over that chunk because this one on this all the way on the left is now the size of this middle one and the one on the left. So we've consolidated it into one. And so this is effectively like this vulnerability. It's that in here, like we're not checking that like that the stuff that we're pointing to is actually there. And the reason this matters is that say you can control some of the data that's in here. Like I can overwrite the previous and the next pointer here. It's writing these values. So it's writing, it's following these pointers and it's trying to write. So if we can control these, we can turn this into a write what where primitive. We can control where it writes to, and we can control what it writes. So I don't think that we need to care about this branch, because I think that we're always going to end up taking this one here in this case, and then we're always going to end up taking this branch here rather than this one. If it's not in use. If it's less than 1. Maybe it is different. If it's this is the stuff that we're not going to do anything here, or we're going to probably just keep following. We're not doing what we care about here. So we're probably not going to take this ever. We're always going to take this branch. And then here, I think we're always going to take this branch, at least in this challenge. So I'm going to go back here. I'm going to get rid of this. We don't need this code anymore. And if anyone has any questions, feel free to ask. I'm happy to kind of go into any more detail about why this is the way that it is. This is definitely not my area of expertise. I'm pretty new to heap exploitation, but I finally feel like I have a relatively decent understanding of this attack, and I can maybe explain it slightly better than what I have already. So knowing this, I'm gonna kill that. We need to create this such that we can write some data into the right spot. So I think what we end up wanting to do we may need to make a fake chunk on the heap. Or we might be able to do it just within the metadata itself. I'm a little concerned that we're not going to be able to get the data right, or we're going to end up fucking stuff up. So basically our problem is that we need to get it so that we don't overwrite the end result. So we know a few things. We know that, let's go back to here. Our return pointer on the stack. This is when login returns back to main, which is the calling function. We know that the address is right here. So return address is right here at 439.012345678 So 439A. Oops. So returns at 439A. We know that unlock door is at, and this is the function that we want to call, at 4564. So what we want to do is we want to get this address right here written to here. So the way that you typically see this vulnerability exploited, I believe, is you create a fake chunk on the heap. So like when you have some space to write to, you end up creating like a fake chunk. And that might be the approach that we take here, rather than trying to like make this all work. And I think that's because you need to have still some like valid next and previous pointers. Otherwise, we run into the same problem that we've been running into, which is you end up overwriting like bad shit. So this is most likely the thing that we want to utilize, this write. And if we look here, this is probably the best place to do this. This is a snapshot of our heap. So if we look here, we can set the next pointer. So we're not going to be able to do it here because we can't control C. We can theoretically do it here. So if we don't use a fake one, we can overwrite this such that this previous stays the same. This next becomes the value we want to write, and yeah, this is why we need a fake chunk. And I wonder if it makes sense for us not to handle the consolidate. I guess we do need it to handle the consolidation, because if we don't, it will never do the unlink. Because I think if it doesn't consolidate, it might just set the value to be on one sec. We want to look at 4560. So 45. Yeah, so it ends up just jumping back to here. So this is effectively a no-op. So that's there, and then four, 5, 2, 4, 4, 5, 2, 4. It's going to do some similar logic here, but backwards, basically. Cool. All right. So let's turn this into something that we can actually use. My session expired? No. We'll come back. So we need the next pointer. We need the next pointer. So basically we would need, you know, this to be the 439A. And then sorry, we need this to be 4.3, or oops, I'm in the wrong spot. We need this to be 439A, and this to be our address that we want to write. I'm concerned that the second consolidation is going to fuck things up, but we can get to there when we need to. So we know we have 16 bytes, so like 1, 2, 3, 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 bytes. And that gets us into the previous. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. The previous, we're going to want to keep the original one. So that's going to be 0824. And then this, our next. It's 9A43. 9A43 2100. All right, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. And here, we're going to need a valid value for previous. And I think that this ends up being the same thing. Because the values are the same. No, it's because it's there. We might end up wanting to swap this with 2408, but we can do this for now. So it's 1E24. And then we're going to do the value on our right, which is 6445. And then we're going to need 9C1F. All right. So using these values, this might provide the correct attack. So we're going to set our breakpoint. Where is login? Set this here. I'm going to reset this. I'm going to continue, and we're going to try this out. And then the password. I hope that we can write enough here. All right. So we're going to continue. We're going to do step into free. And basically, if we finish out of here, we're hoping that right here is going to be the address for unlock door. So finish 241E. We overwrote the right thing, but we overwrote it with the wrong data. We need to... Where did it get the 241E from? Oh. Is previous, right. Okay. Let's try this one more time. Step and finish. Did I? Oh. it's going to here, which we don't have control over. Yeah, so this is little endian. All the values I'm putting in are in little endian. The reason this is failing right now is because it's following the pointer to right here, and it's grabbing the value from here, which we don't have control over. So this is why we need to create a fake chunk, most likely, and direct it to there. So if we go back to our code, so it's already done this, and so C next is now pointing to like the next, which here would end up being this, and so this previous is going to be here. All right, so well, I mean we can still fix this. It just means that like our username is going to end up being like a fake chunk. Or our password. So, what is the best way to do this? Did I? Hold up 1 second. Maybe it didn't copy. Yeah. Next. Let me jump up here really quick. So next ends up being here. So next prev next. Yeah, because that's pointing there, which makes sense. All right. So here is our problem, is that we're probably going to end up running into this consolidation code instead, because we're going to consolidate backwards. Realistically, this should work more or less the same, except for backwards. C preview size. C next. And oh yeah, no problem. I mean, we're all here to learn and get better at this stuff. So I mean, I appreciate it. Any help or ideas, but this should be the correct logic. And actually, it would be C prev size plus equals C size plus 6. Next, and C next prev equals C prev. Yeah, so this should be the correct logic for consolidating backwards. So if now, one of the other things we can do is we can stop consolidation because we control the size field. So we can just like say like, oh yeah, it's not in use, or it is in use, which may be what we end up wanting to do. So we're gonna set up our fake chunk. We need to have a backwards pointer, which probably should point to something real. I guess we could do like 2408. Our next pointer So let's see. So the first thing that we're going to end up freeing is this right here. And it's going to consolidate backwards. So the backwards consolidation logic is right here. And we're going to do... So So I think this is the right that we're going to end up using right here. Because we can control the That's what I don't get is why we're not able to do it just here. Because at this point, one E24. Oh fuck. At this point, we're no longer pointing to there. Like, can we do this without a whole fake chunk by just overwriting stuff that we have control over? Yeah, we can. We overwrite this. This ends up being the value. So we go six, 4, 4, 5. and then this ends up being, needs to point to there. So it would be 0E24. Step finish. How is that still doing that? Step. That's the only thing I don't understand is the only thing pointing to it is right here. But why is anything pointing back to there? Maybe I'm missing. Continue, and I guess maybe I'm not looking at it when it's before it fixes up addresses, and it still has something that is. All right. So we're at free. Like, I don't understand how it would even get this value after this, because it's freeing this, and our right here, and our pointers. I guess the other thing we could always do is just put our own shellcode there and like be done with it. it changed because of the free. Yeah, so it's changing because of the free. I guess, do you know anything about heap exploitation? I can start back at like what we're doing. I went over that a little bit earlier, but it might be a good time to go back to that if it's not clear like why this is happening. Sure. So we reverse engineered the free function, and basically the way that this works is the heap is set up like this. We have this heap header, which occurs. Let me get to a fresh state. So it's oops. All right. More or less. Actually, you know what? We can just do it from here. So this is what the heap looks like when it gets initialized, but we don't allocate anything. It's going to get lazily like actually set up. So the beginning of the heap, we have a couple pieces of information. I think this is like the pointer to the first chunk in the heap, and a chunk is basically just like a section of the heap that's been like passed out for malloc. This points to the very first chunk right here. No idea what this is. It's data that doesn't seem to change. Maybe it's the slab of heap that we're in. I don't know. Not sure yet. This tells you whether or not the heap has been allocated or set up. So like right when you start the program, it's set to 1, which means it isn't, and then it gets cleared the first time you malloc. Because what it's going to end up doing is like setting up this stuff down here, which we'll get into in a second. And then this is some padding. I think doesn't ever seem to change, and it just happens to be there. I think what it does is it allows it to fit into like this structure effectively. And this struct is like what we see like chunks take, and then like the last little area take. And so we see our first allocation here. This right here is the beginning of our first chunk. When you call malloc, malloc is going to give you a pointer to here, which is the beginning of the user data. So there's 6 bytes before that. They make up some metadata for the individual chunk. And that metadata will look like this. We have a pointer to the previous chunk, and we have a pointer to the next chunk, and then we have a size field that tells you like how big something is. And so effectively what we're building is a doubly linked list of chunks in the heap. And the reason you need that is because you need to be able to do compaction, both forwards and backwards, because you don't want to get the heap into a state where it's really fragmented. If you do that, you end up like getting these little tiny pieces of heap, and when you need a larger amount of space, you're not able to give it like space. So when you call free, it's gonna try to consolidate. Like if the previous chunk is not in use anymore, then it's gonna try to compact it backwards, and then it's gonna check if the next one is in use. And if it's not in use, then it's gonna compact it forwards, and it's just growing and growing, trying to get things that are next to each other to like move together into a single chunk. I don't know what the algorithm is for malloc yet. We haven't really gone through it yet. But my guess is it's first fit. So it's going to iterate through the linked list forwards from the starting point to the end, looking for the first chunk that will fit the space that it wants. And then it will carve out the necessary space from that first chunk and hand it off to the user. Again, just guessing at this, not 100% sure. Your teacher explained that? Yeah, I mean, so I don't think I ever got really explanations of the heap in my classes. I wish that I had. Like just getting to this point for me was really difficult, and took a lot of reading and like just scratching my head at like what actually was going on. And then at the very end, you end up with this last little like chunk, and this tells you you have a previous pointer just like we have up here, and a next because it has to fit the right structure. And then this is like the total space remaining on the heap, and then just some padding here to fill out like what would be like the user data. So we see that here. Where are we? We see that here. This is our total remaining space on the heap, like 1F9C. This is our next pointer. This points back to the front of the heap, and this points backwards to the last chunk in the heap that isn't like the, well, I don't know what to call this, but it's like just like the end metadata effectively. And so what we're taking advantage of is the fact that we can write past the end of our user data, like right here and right here, and we can write into these forwards and backwards pointers, and we can take advantage of that to overwrite arbitrary places in memory because of the consolidation logic here and here. If we can control the previous pointer or the next pointer and give it a value we want to write to, and then update the next or previous chunk's pointer that's going to get written to there, then we can set it up to do that right. So what we're doing is we're setting up a fake like previous or next pointer as our stack address, and the overwriting a next or previous pointer with the address we want to write. So when it goes to do that consolidation, it ends up writing to the stack rather than the actual chunk and filling in the value that we want. The problem right now is that we're not putting in the right data in the right places, and so it's writing the wrong data to the right space. Yeah, no problem. So I think that this logic is correct. I mean, effectively, this is what it should be doing, but not 100% sure. Like we can. I don't have a donate button because I don't have anything set up for that. I've been on Twitch not long enough, so I don't have like partner status or whatever they call it or any of that. So like I don't really have any of that. I do want to build some classes at some point in time, and those probably will eventually go up for sale. We'll go much more in depth. But right now I'm just doing this for fun, hoping people can learn some stuff and get interested and want to play with this too. So we can go back in and we can verify this logic is correct. Yeah, nice to meet you too. But we gotta figure out why it's reading this. I think it's coming from here, and we unfortunately don't. Like, can we write arbitrary memory? We can read. We can't write. Right? Oh yeah, we can't write to register or memory. Maybe that's the move. Is we end up doing this right, and we see if that fixes it. Either way, I mean, like if this is where it's getting it from, we're not going to be able to control this value. It's just not something we can do. But we can at least know what we have to change. So I'm going to go back and I'm going to make these 4 ones again. And I am going to reset that. Continue. Set that there. Continue. And we are going to try this. Continue there. We're at the free. We want to update this address. And so that is going to end up being, what is it, L? Read your adder, L. Let's see. We want 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. So it's 24, 0A. And we're going to write 4343. Could not find label. Okay, so that worked. Let's see if this ends up writing 4343 to right here. Finish. Oh, what the fuck just happened? Something bad happened. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. A. Oh. 92.4. That's backwards. Zero, 8, 2, 4, 9A, 4, 3. No, that's correct. 9A, 4, 3. 2, 4, 0, 8. 2, 4, 1, 2, 3, 4, 5, 6, 7, 8. Probably try to follow that pointer, and bad things happened. Okay. Or this is not aligned right. I can tell that right now. Continue. That's definitely not aligned right. Yeah, there are too many, not enough A's. There. Which would explain like why that failed before. If we look here, this now is correct. We can try the L expression again. And it's interesting that it's still... Huh. Oh, because 434 is not mapped, probably. We can do 4, 4, 4, 4. So we still have this address here, which is good. Nothing is broken. We do want to make sure that our unlocked door isn't fucked up. It's not fucked up. So that's good. We do want to figure out why that's getting written, like the value is getting written there. We can try changing this one. Yeah, I don't understand like where this is coming from. Like we could change both, and even that, like I don't know if that's gonna like. Like, where the fuck is it coming from? Unless it's like calculating based on size, which is definitely possible. Um, it's one of the reasons why the size fields are there, is it will reach back like that many bytes, and we haven't actually looked at this code. It's possible that it's looking at the size. Maybe that's the move. Maybe we should do that. Although within here, I don't see how that would be happening. Well, so R14 still has this. Why does R14 have that? Like, where does it get that from? Oh, I mean, we can set a fake chunk. C next equals so we can do this, I guess. So equal, so it's gonna be 0e24. Back these up real quick. So 0e24 e24. That's gonna point. Yeah, man. Have a good night. Have a good night. Feel better. Hope you recover from that. I can't imagine having to deal with that right now. So this is going to end up pointing back to here, to our user data. And then from here, we're going to be able to make some changes. So our points to next. So 1, 2, six, 4, 4, 5. And I think this ends up maybe being what we need. And then we need to make this 2100. Oh, actually, we don't even need it to be that. Oh, yeah, we do. It needs to be in use. And try it both ways. Although, so the problem here is that we're going to end up overwriting stuff here, I think. Let's give this a try. continue. And then continue, and we're going to go out here. So we're still writing 241E, which I have no idea where it's coming from. So C next is getting written here. Oh, because the pointer is that. Well, we could try making it not in use. Yeah, I mean, I think it's time just to walk through it and see like why we're getting this value there. So step. We're subtracting 6 from the start of the pointer. 2424. for 1e. Yeah, I think that's what ends up happening is because of where because we're calculating that, it never gets it out of R15. So it adds 4 to R15, R13. Six to R13. Move 13 to 4 of R15. Which does two from R14. Four, 3, 9A. 0 into into 2 from R15. Yeah, so the value is just there still. It might be the other branch we need to do is we So pretty much no matter what, we're never going to be able to write that there. It's all doing it based off of here. So we may not be able to do an arbitrary write. from there. So shellcode will work here. Like we can solve it with that. And this is what, 2, 4, 6, 8, 10, 12. I mean, technically we only need 2, 4, 6, 8, and let it crash. Two, 4, 1, E. Yeah, I mean, the only problem is we end up writing bad values here. We might have to go reverse this and do the backwards consult. Well, we're not consolidating backwards though. And I don't know that we have the opportunity to do the overwrite to do that. Twenty-four, 24. One E. Move 4 bytes from, so it moves the size into R13. don't care about any of that. So then R14 is going to have the previous. So like we could, I guess, force it to consolidate back. Because we can control that pointer. Okay, well, let's try this then. Hey, how are you doing, Barkink? And thanks. So this is now not in use. It's our fake chunk. And we want to point the previous. So we're going to point this at 0E24. Cool. Yeah, I don't really have a set schedule, unfortunately, right now. I'm off work for the next like 2 weeks. So I'm probably going to be doing a bit of streaming over the next 2 weeks, but I'm hoping to kind of get something a little more formalized once the new year starts. Mostly just something like running through these and trying to get through it. But once I have something a little more stable, I'll have like a schedule up on Twitch probably, and then all the videos are getting exported out to YouTube for archive, and so anything there will be, everything will be there, like not live. Cool. Yeah, I'm happy you like it. So see next. See. Let's try this. This is gonna not be useful yet because our pointers are bad. But we are setting up the correct reference back. And we may not need to overwrite any of this. So now we're doing the other branch of our consolidating backwards. This is what, 2, 4, 6, 8, 10, 12. Yeah, I think it's probably right. Continue that. And then this should just be 4242, so we don't care. All right, we're gonna single step this. We're subtracting 6 from R15. Moving our the size field into R13. We're getting rid of the, all right, so 240E ends up being right here. We're moving the size field into R12, so that should end up being 20, which it is. We're gonna do a bitwise and jump not 0, and so we're not taking the jump. Cool. Yeah, I spent so many hours on the Nat Slitstream stuff trying to get Sammy's code working. And like no offense to him, like the demo was really cool, and like when he put it out it was like really awesome with like a good write-up, but like there wasn't really like a good thing to like just test it and verify like if your gear worked or not. And like I couldn't tell if my equipment was not vulnerable or if there was like something else going on. But I'm happy that others found that useful. Like I said, I spent a lot of hours just trying to figure out if my home network was vulnerable, and get something working, and like finding I can't remember his name, but the other person who wrote the code that I based mine on, like that was a lifesaver, just because it made it so much simpler. Like I said, like I'm definitely not like a networking guy. Like I don't know shit about networking. So like I'm sure that you'd have like probably a lot more to add to it if that's like your bread and butter. So we're gonna add 6 to R12. That's gonna move us to and we're gonna add R13 to R12. That ends up being hex 46. And then we move that to the size field of R14, which is 240E. And then we move the Thanks. Yeah, I mean, I haven't really been consistent in streaming. I've been doing it on and off for like a while, but like my times and dates like haven't been consistent, and so I think it's really hard to like grow a channel without that. And the content is pretty like all over the place, like everywhere from like just hardware hacking to designing like hardware to this kind of shit. And so I also don't do a ton of like self-promotion, so I think it's kind of hard like if you're not doing that. So now we're taking the current next pointer and we're moving it into the previous next pointer. So R14 R14 is pointing to right here. It's going to end up writing that there. (439A). Yeah, I'm happy to interact with people. Like, if you got questions or just want to talk, like I'm here for both. So we moved that address to there. I don't know if that helps us in any way yet. We're now going to move the next pointer into R13. And then, what's in R14? R13 is 439A. So we're going to write to here now, but we're writing what's in R14, which is something we control, but not particularly useful. Maybe the move is that we end up just putting the value here. (439A). What was our return address here? 6445. I wonder if this will just work. We're gonna end up writing some garbage onto the stack, but like, we don't really care about that much. As long as we don't break anything. We just did something. 6435. I think we just did it. Did I type that wrong? Yep. Yeah, okay. I think that's it. I think that's the solution. Okay, so something's broken here. So we ended up doing the same thing we did before where we overwrote code here. That's bad. Could be that we need to link in this this fake chunk and four, 5, 6, 4. Yeah, so we fucked this up. 301200. I think these are the bytes we overwrote here. So 5, 3. It's all of these bytes we overwrote here, or some level of them. All right. So the interesting thing about this, though, is that if we use this, we're in a good state up until the second free. And so maybe we just need to use the second write to like put different data there. We could theoretically also make this already freed. I don't know if that would be good or not. Yeah, definitely. Do you know about heap exploitation at all? Because I think that's the point to start at. I've got this whole like doc I've been putting together that I've gone over a couple times now, and like I can do this again, but I don't want to like dive into it if you already have a good understanding of like what we're doing and how this works. Open the window real quick. Cool. All right. So basically, what you need to know about this is that this exploit is based on the unsafe unlink exploit from glibc 2.5 and before. I went into like how this worked and we looked at the code before, but we'll explain it right now. So when you create the heap, like when this thing starts, this is what the allocated space of the heap looks like. What this part here points to the first element on the heap. This is the first chunk, and the chunk is just like some space that's been allocated when you call malloc. It'll hand back like the pointer. This, no idea what this is. It doesn't seem to change, not really clear. This tells you whether or not the heap has been initialized and something's been allocated on it. And I think this is padding, so that it fits the structure that we see here. At the end of the heap, once you've allocated something, you're going to see this. And each one of these are 2 bytes long, but basically it's meant to match this structure. And this structure is an individual chunk. A chunk is going to have 3 pieces of metadata that go with it. You have a pointer to the previous chunk. So we're building up a doubly linked list, and all the chunks will go in order of when they got allocated. You have a previous chunk, you have a next chunk, and then a size field. The size field doesn't seem to be like actual size, and I'm not exactly sure why it is the value that it is. But the only important thing you have to know about it here is that the least significant bit of the size field determines whether or not the chunk is in use. And the way that that works is like on most modern like malloc implementations, you can't request a chunk that's like 6 bytes or whatever. Like the smallest you can do is like whatever like the word size is of the system or something like that, or like the register size. So we don't really care about like the last bit because it represents just a small amount of data that like it's not usable. So they reuse that bit as a space savings to determine whether or not the chunk is in use. And we'll see that here, like these 21s. So this typically like on a heap implementation, you'll see like this means like the space being used is 32 bytes, and then this one is being like in use. Different implementations are gonna be a lot more complicated, but like this is just simple doubly linked list. All chunks in here are present, and then at the very end of the heap, you're gonna have this like last little like fake chunk, and it's gonna have a previous pointer, so it points back to the chunk that is like the end, and the next pointer points back to the beginning of the heap. And then this is the space that is remaining on the heap that's available to allocate from. Now, one of the big problems with the heap is that you don't really know how long data is going to last for. I think the last time I spoke a little bit about like lifetimes of data. The lifetime of data on the heap is from when you allocate it to when you call free. And you're not necessarily like allocating and freeing stuff always in the same order, like you would for like an automatic variable in a function. So you really don't want fragmentation of your heap, because you end up with all these little holes where you can't allocate like large chunks. So it tries to do what's called consolidation. If you call free and the chunk in back of you or in forward of you is free, it's going to consolidate those into one bigger chunk. So next time when malloc runs through, it can say, oh, I'm at this point where I have some free space. I'm going to carve out a section of it that's big enough for the amount being allocated, and then move on. So we have two opportunities to do this. Usually you go backwards and then forwards. So in this code, we have an overflow. It's on a Stack Overflow to heap overflow. So we're able to write more data to arbitrary sections of the heap, not arbitrary, but sections of the heap that are there, then is allocated for us. And what that allows us to do is, because these are all allocated, right after each other, all these chunks, right after this size field is where our data is going to end up being. We fill all of the data. We can then write into these previous and next fields, and that allows us to change the pointers that are followed when it tries to do the consolidation. It also allows us to change the size field, which allows us to control whether or not the heap implementation thinks that a chunk is in use or not in use. So right here, we're overwriting 16 bytes. This is the area that's been allocated for us on the heap, and then we're going into the next chunk, and we're modifying the previous address here, the next address here, and the size field here. And so we're setting this to be like in use. In this case, why are we not... Did I screw something up here? So great. So one of the things you can do, and like the way that this attack was performed like way back on glibc, was you could create a fake chunk, and you could point the previous or forward pointer to that fake chunk with data that you control. So this is data that we control. We can write whatever we want here, and we can reference back to like here, and like we have now forwards and backwards pointers that we can point to like literally anywhere on the system. And so we tried doing this where we can this is already in here. So what we did here, so I don't remember why I did what I have right here, but anyway, if we go forward here, we're gonna see that we can write data into here, and it's gonna be fine, I think, during the first free, and then it fucks it up after. Oh yeah, the 4141, 4141, 200. This is effectively like a fake chunk that we're not using right now. We're gonna jump into this, and then so you can see here like we've overwritten this address on the stack. This is a return address, and we've now written the return address of unlock door to the stack. But if we go and look at unlock door, we've corrupted it. We've overwritten data here because it's tried to fix up that data. So what we need to do is basically trying to take it back. We're trying to take back the data so that it's valid. Basically, we want to get control flow. So this is the pointer that we're trying to hijack. We have successfully done it, but in doing that, we've also corrupted the function that we actually want to run, and so that's bad because when it starts executing there, it's gonna fail. Now, yeah. Like, and the thing is, like, we don't control the data that gets written there, so like we couldn't just put like nops there or anything. So I think we're missing a step. Is effectively like what the problem is. So what we're probably going to want to do is we have this stuff that we can control here, and this is our fake chunk that we're going to have. It's not in use, and so it's going to try to consolidate backwards with it. Should we take it somehow where it was in the first place? So the goal is that we don't end up corrupting it. And we can do that by adjusting the exploit somewhat so that we're doing it slightly differently. Because we don't have the ability to write arbitrary data here, like we sort of do, but we don't have enough control over it right now. We can't just like fill back in the shellcode here. Or effectively like write shellcode that fills back in that data. So what we're going to end up trying to do is fix this exploit so that we don't end up overwriting here, but we do overwrite right here. And I think what ends up happening is we rely on either consolidation in both directions, or we rely on the consolidation behavior of the two different allocations that we have. And that allows us to basically get to a point where we write the correct data in the correct places without fucking anything up. Sorry, give me 1 second. Dealing with the dog. So I think this is part of the problem. I think this is the wrong logic. I think this should be this. Give me 1 second and I'll be right back. All right. Sorry, 1 second, just a couple things. All right, so I think that this code was wrong that I had done, because we need to change the previous's next pointer and point it to C next. And we can go verify this in a second, but I think that this is correct. And if this is correct, then I think I know what we need to do. So this is going to end up pointing to here. So we're going to point back to here, and this is going to be 240E. So B24. So this is our previous pointer. We're pointing back to there. And we want this to be where we're going to write to, which is 9A43. And we're going to write the address of the return there. So it's 4564. I think we might need to put real pointers there for the previous. Not 100% sure what the state of this linked list is going to be in, and it might cause things to break, but so we can go here and step finish. So that didn't work. I think we did something bad. We ended up overwriting unlock door, but we didn't overwrite the return address. Which means Could be that this logic is wrong. Doesn't see. Next prev is let's step through this. All right. Next step. And the beginning here, we don't really care about. We already know what all this does. We're basically getting the right pointer. And then size of our 14. We're checking if it is free. And now we're going to do this. So, all right. So we're going to add 6 to R12. Then we add R13 to R12. Hit 46 hex. Move R12 into the size field, which we don't really care about, which updates there. We're moving 2 bytes from R15 to 241E. So right here, we're moving this to the I'm pretty sure the logic is just wrong. So the next of current which is this, is getting moved into the next of previous. That gets moved into there. So next of okay. So this is going to get moved to here. Which we don't really care about. It's not dereferencing this, which is partially the problem. And then it moves next of current into R13. What's R14? R14 has the address. So the next pointer gets moved. The next pointer of current. So we're going to write this value to the next one of current. I think we did this backwards. 9A43. So putting this value here, I don't think is going to help us necessarily, but we'll do it just to fill it in. 6445. Because what we're going to end up doing is we're going to end up writing. We're going to write this value to here, which like isn't the end of the world. Like, we could put shellcode here. Like, we could put, like a jump to, a jump to here, if we wanted. And that would be fine. I just feel like there's a better way to do it. And continue. I don't think we need anything there. So do that, and we're going to finish. What did we just do? Oh, we broke there. That's why. So we now have something we control there, at least. And it's going to end up hitting like 4141. We can go to the assembler and we can see like what's jump. I think it's just JMP. Yeah. What does it take to do this? Bad operand. What do you mean? Can we not do a... I guess we could do a call. Yeah, so like theoretically we could do, what is this? 1, 2, 3, it's 4 bytes. We might not have enough space. Well, no, we do, because we don't care about this. As long as this is there, we're fine. And we can. This is all chill. So let's go here real quick. It ends up being so we might be able to just do this. So now we're just gonna end up jumping to our fake code here. Continue. 42, 42. Continue. Step. What happened? What's an R15? 24 1E? Twenty-four 1E. Oh. It needs to be a valid pointer. 439A. Did I? What is that? What? Four, 3, 9A. Where are we? Two 4E1. Am I off by a... I think we forgot. Yeah, we're off by 2 bytes. Or, yeah, 2 bytes. And this needs to be that. So I think this is probably gonna work. I think there's a better, like, nicer exploit than doing this. So 24E0, 240E, and that's our call. Finish. We're unaligned. Oh, whoa. Did that... We're pretty good here. The 240E. anything in like this region changes, we're not doing hot. 9012. Oh, I think it wrote a 00 there. Unaligned means that the instruction that we're jumping to or trying to execute is not at a like a 16-bit boundary. So in MSP 430, all of the opcodes are all aligned to 2-byte chunks. So we're jumping into something that's like not aligned. So if we do finish here, we're gonna pop those, and we're at this 9012, and this is probably no longer a call. 9012 6445. Yeah, so it's trying to jump to like to 00, which not good. So why is there a 00 there though? Oh, it's copying the it's copying the next pointer of the it's this, I believe. It's copying, so C next 439A. It's copying, I think, this 00 into there. I wonder if we just overwrite into the next, the end here, and maybe we can do it with both. The other thing we might be able to try is setting, well, I kind of think it's going to be a no-op. Where's our free? This doesn't really help us because we're always going to make that 0. So we can go back and verify this behavior and make sure this is correct. All right. We're stepping in. All right. So, this is the size fix up. R12 into, this is the new size. Then we're doing the next of current. Current, previous, next. So yeah, we're writing the, that's correct. And then we're moving the next of current to R13. Into, and it's going to follow so the next of current into R13. R14. R13. So yeah, the next of current Yeah, okay. So then this is R14 is the previous. Yeah, so I mean this is right. It's moving this into it's moving this into whatever the next is. Which in this case it's not there. It's gonna be 2434. Or no, because we've overwritten it with that. So then R14 goes to 439A. Then R15, 241E, 241E. E goes to there. R15, 240E. And then 2 bytes in from there. So right here, 439A. Goes into R14. So size of R13. So this is going to fail, so we're not going to consolidate forwards. Yeah, so 0. So then we do the size field of R15, which is now 46. We add 6 for C. And we write R13 to 4 bytes from R15, which ends up being right here. So we could go back to the shellcode example, and we just need to subtract 6 off from the value that we put there. Or we need to subtract off hex 20 and hex 6, I think. We move, what is this, from R14. (439A), and that's where the null comes from. Yep, there's our null. And then we move R15 24.0E into the previous of R14. So let's Google this. Glibc unlink tac. This is what it's based on. Corrupted. Detected as freed. So this is different. We're so close. Yeah. See. I guess we could use zeros here and not end up adding stuff, but I don't know if that's helpful. And like this always ends up being 0, 0, which is a problem. What is 0, 0 disassemble to? RRCPC. Yeah, that seems like it's not good. Like, we wouldn't want to run that. Like, it's not a NOP, I don't think. There's no way we can get control of that data because that's straight from here. So like we would never be able to write that. So we don't get to write the metadata for the first chunk. So that ends up being turned. So like we never end up going into this branch because the next pointer the next pointer that we're pointing at, which is this, sorry, the next pointer is this, is is 0. 439A. I mean, I guess we could change that to something else, and Does it help? Maybe we make it point to the first chunk, and then we modify the metadata in there. Like, we can force early consolidation, I guess, but I don't know that that's helpful. I think we can get rid of all this. This is not useful anymore. Two, four, one. Maybe we can do something else where we can update it. I don't know. I'm at a point where I am trying to think through and think about it from a different way. I don't know. We have control, and that's like one of the big pieces. The problem now is that I'm stuck trying to use that control to do something like meaningful. At this point, anytime we've done something where we can write into the address we want, we corrupt the function that we care about, and when we try to put shellcode in there, we don't have enough control to stop it from mangling stuff. There might be something that we need to do using both of the allocations, and so on both frees we can get something correct, or maybe we have enough control to force a forward and backwards consolidation. and that gives us enough where we don't end up ruining the data. But anyway, I need to take off soon and make some dinner. I think taking a look at this with fresh eyes, now that we have like a better understanding of like exactly like what the code is doing for here, I think this will make it simpler, and we just basically need to come back to this and like redo it. But yeah, I don't have like an answer right now, and fortunately I'm at the point where I think I just need a break. So thanks for joining, everyone. I think I'll be on maybe tomorrow or Thursday. Not exactly sure yet what the schedule is going to be like, but we'll definitely spend another session working on this later in the week. Hope you all have a good night or morning or afternoon, wherever you are right now. And I'll see you next time.